much for the introduction, and thanks a lot to the organizers for inviting me. Today I'm going to be talking about a project which is joint with Louis Esser, who is a postdoc at Princeton, and with Joaquin Moraga, who has been here at this conference. Right, so the title is Symmetries of Fano varieties. So throughout we're going to be working over C, and I should also say I'm very receptive to feedback or questions. If you have any questions or comments, feel free to interrupt at any time. And if my volume or handwriting gets too small, feel free to just tell me to write bigger or talk louder. Okay, so I'm going to start off with an introduction. And so maybe some vague question that we can start asking is, how big can the automorphism group of a Fano variety be? Okay, so I guess as you know, we have this sort of trichotomy of varieties based on the positivity of the canonical bundle. And sort of in dimension 1, we have this bound on the automorphism group of a genus at least 2 curve, which is at most 84 times g minus 1. So in particular, in the kx positive range, this is always a finite group. For kx trivial, this is the automorphism group is going to be the semi-direct product of translations and some finite group. And then in the Fano case, we only have P1, so the automorphism group is infinite. And in fact, in any dimension n, we always have projective space is some Fano variety. So we always have this large infinite group PGLM plus 1 here, whereas sort of in the general type case, there exists, I guess, a uniform bound in terms of the volume. But in particular, for these kx positive varieties, they're always finite. So I guess this is the Hagen, McKernan, and Schuh. Right, but so maybe already we can see that this question is maybe not a well-posed question because the automorphism group of a Fano variety is often infinite. So instead, we're going to ask for a different size of how big this group is. Instead, we're going to ask how non-abelian can the automorphism group of a Fano variety be. Okay, and so to make this question a little bit more precise, we're going to need some definitions. Okay, so first, we say that a group G is Jordan if and only if there exists a constant J such that any finite subgroup has a normal abelian subgroup of bounded index of G has a normal abelian subgroup of index at most J. So in a sense, this is some bound on how non-abelian a group is based on how when you take any finite subgroup of it, if you can find some abelian subgroup of not too large index. And then we can also make a definition for a family of groups. So a family curly G of groups is uniformly Jordan if and only if every group straight G and curly G is Jordan, and moreover, the same constant works for all these groups. And moreover, the same constant J works for all straight G and curly G. Okay, and so why is why does this property have this name? Well, so this is because of a theorem of Jordan from 1878, proved that GLN has the Jordan property. Well, I guess he didn't state the theorem like in this way that I'm stating it. And then more recently, Collins has got an effective bound for what this constant J is. So this is Collins in 2007. I think for n at least 71, the Jordan constant for GL and C is n plus 1 factorial, and it's given by the standard representation of the symmetric group of order n plus 1. Okay. So he has a list, but you can get other groups that aren't the symmetric group that sort of make this big constant bigger. So for small n, you can have some pathologies with somehow for n large enough. Like the worst thing is symmetric group. Yeah. Thanks for the question. Okay, and so maybe just to remind everybody what the standard representation is. So we have S n plus 1. This acts on C n plus 1 by permuting the coordinates. And so you have a one-dimensional invariant subspace spanned by the sum of all the basis vectors, and then the standard representation is the complement. Oh, thank you. Okay, right. So this is for GLN, and then more generally, this property holds for a larger group of groups. So I'll just state the theorem, and then I'll say who proved what part. So this is due to Prokhorov, Shamarov, and Birkar. So what they showed is that for any n at least 1, the family of groups so a set of Beer X for X in n-dimensional rationally connected variety is uniformly Jordan. So in particular, why is this relevant to our question? Oh, and I guess I should say, first I should say throughout this talk, Fano means KLT. A KLT Fano variety is rationally connected. I guess in the smooth case, this is due to Kolar, Miyaoka, Mori, and then it was generalized to KLT case by Zhang. So in particular, this includes all n-dimensional Fano varieties are included in here. And furthermore, the birational automorphism group can't give you any extra information than the automorphism group. So in particular, this this includes the set of automorphism groups of n-dimensional Fano varieties. Okay, and so this was, right, so who proved what piece? So Prokhorov and Shamov, they proved this, assuming boundedness of terminal Fano varieties. And then, as we all know, Professor Birkar proved BAB, making this result unconditional. Okay. Okay, so are there any questions about any definitions or anything so far? Okay, so one particular consequence is that for any dimension n, we get a bound on the maximal semi-simple group G that can be contained inside the automorphism group of any n-dimensional Fano variety. Where here by semi-simple, maybe this is not, I don't know if this is standard group theory terminology, but this means that it has no non-trivial normal abelian subgroups. And so one example of such a semi-simple group, which you've already seen, is this group, the symmetric group, which for GLN, at least for n large, realizes the Jordan constant. So yes, in particular, get bound for the maximal symmetric subgroup of the automorphism group of any n-dimensional Fano variety. Okay, so maybe I'll introduce some notation. So I guess M of n is going to be the largest K such that SK injects into the automorphism group of some n-dimensional Fano variety. Okay, so then, right, so maybe we can just start off with, okay, so we have this, some bound. It's not an effective bound, but we have some bound. But maybe we can first try to give some examples of like largest symmetric group actions on Fano varieties. Okay, so maybe to start off with the first example. So first we have the symmetric group of order n+1 acting on projective space of dimension n by permuting the coordinates. But we can do a little bit better than this. Right, as above, we have this standard representation of the symmetric group, so we can go one higher to Sn+2, acting on projective space by the standard representation. But then, in fact, among rational varieties, we can even do one better and get an action of Sn+3. So instead of acting on projective space, it's going to act on this complete intersection of two Fermat hypersurfaces. Such varieties of these shapes will appear throughout the talk, n+2. So this action is induced by the action by permutation of coordinates on the ambient Pn+1. And so this variety X, this is invariant under this action. And so X is isomorphic to a smooth quadric. So it's rational. So this exhibits one embedding of the symmetric group of order n+3 into the Cremona group of rank n. Okay. So in any dimension, we have this Sm plus 3 action. And so then we can ask, is this action maximal? And in low dimensions, the maximal actions are classified. So for n equals 1 and 2, Sm plus 3, this is maximal. Okay, so I'm just going to make a table of some known results. So here's going to be n, the dimension m, and the maximal order of the symmetric group, and the maximal examples. Okay, so for dimension 1, the maximal is plus 1, which is 4, and I guess the only example of a one-dimensional Fano variety is P1. But then it turns out in dimension 2, again, the maximal is n plus 3, which is 5, and there are 3 maximal examples. So there's P1 cross P1, there's the Klebsch cubic, and then there's a del Pezzo surface of degree 5. And I guess where I learned this from is a paper of Dolgachev and Iskovsky from 2009, classifying the subgroups of Cremona 2. And so very briefly, where do these come from? Okay, so the first one, P1 cross 1, you can see this acting on this sort of 1-2 Fermat complete intersection, which we saw before. The Klebsch cubic is defined similarly, but instead we take the second equation to be degree 3. And then for the del Pezzo of degree 5, we can see this by identifying this with M05 bar, which is isomorphic to P1 to the 5 copies, divided by SL2, and so then you get this 5 acting on these 5. Okay. So in dimension M02, these maximal examples are, all rational, because I guess all Fano varieties dimension at most 2 are rational, but this stops being true in dimension 3. And so in dimension 3, instead of getting Sm plus 3, we actually get 7 as the maximal example. And so then it turns out that, so Prokhorov showed that there's only one maximal example in dimension 3. So this example is so-called symmetric sextic. So it's defined by these 3 Fermat hypersurfaces inside P6, and this is the only one up to conjugation. This is by Prokhorov in 2022. Right, and so then in higher dimensions, the maximal order is not known, and the maximal examples, I guess, correspondingly are not classified. So in dimension 4, this number is at least 8, which we'll see shortly, and there's no classification of maximal examples. And then something else I wanted to point out, which I'll come back to later, is that, so this example in dimension 3, so Prokhorov showed there's only one example, and so this threefold, Beauville showed that this threefold is irrational, which again doesn't happen in dimension at most 2. Okay, and so, right, so maybe next I should justify this m of n is at least 8 for n equals 4. So for n equals 4, this m of 4 is at least 8. So I guess my co-authors and I, we know of 2 examples. So we're going to call these x1, 2, 3 and x1, 2, 4. These are going to be defined by these 3 Fermat equations inside P7. So these are each fourfolds, and they have an SA action inherited from the SA action on P7. So I guess these are fourfolds. With SA actions. Okay, so so maybe I want to pause and make some observations about these examples. Oh no, so far. So so as we can see from the list, and at least in low dimensions, there are only finitely many maximal examples in each dimension. And then furthermore, starting from dimension 3, or I guess in dimension 3, we don't know about higher dimensions, this one example is irrational. So maybe I'll pose two questions. So in dimension n, are the maximally symmetric n-dimensional Fano varieties bounded? And then for question 2, in dimension n at least 3, are the maximally, so here maximally symmetric just means having an Mn action. So are the maximally symmetric n-dimensional Fano varieties irrational? And then maybe a more refined version of question 2 is n plus 3 the largest symmetric subgroup of Cremona n for any n. So why? So as I'll say, as I'll hopefully get to later, so it turns out that Mn is strictly greater than n plus 3 for n at least 3. So I guess question 2 prime would imply question 2. Okay, so I'm just posing these as questions because maybe there is not that much evidence for them aside from these very low dimensional examples. But the first result I want to say is sort of some positive evidence for question 1 in dimension 4. So I'm going to move here. Okay, so the first theorem, which again, everything today I say today is joint with Lewis and Joaquin. So we show that the maximally symmetric Fano fourfolds form a bounded family. And then maybe a little bit more precisely, what we actually show is that we actually show this for SA equivariant Fano fourfolds. We don't show that M of 4 is equal to S8, but if it's true for S8, then it's true for any larger symmetric group. And so let me make a remark here. So this is theorem 1. This is false for SA acting on fourfolds. So I guess we can construct some examples, and basically the idea is that this is the reason this fails is sort of because SA acts on Fano threefolds, so we can do some constructions with taking some projective bundles to create some family of fourfolds with Fano fourfolds with S7 actions where the MLDs aren't bounded. So, right. So somehow it's important that in this result that SA doesn't act on any lower dimensional Fano varieties. Okay. Yes. Yeah. Yes. Yeah, that's right. Yeah. Yeah. And then so it will if maybe the bound is bigger than 8, but the larger symmetric group will still contain S8, so they're still bounded. Yeah, exactly. Yeah, thanks for the question. Okay. Yeah, so aspirationally, I was going to sketch the proof of this at the end of my talk. I guess we'll see depending on time. But there are some other results that I wanted to mention. Okay, so hopefully the proof of this will happen at the end. Right, but what I want to turn to next is that, right, so from this result of Prokhorov, Sharmov, and Birkar, we have this some bound for the maximal symmetric group acting on the n-dimensional Fano variety, but this bound previously was not effective. So something else we do in our paper is we have an effective bound, and then we get better bounds for certain classes of Fano varieties. So this is going to be the second section. Bounds on symmetric actions. Okay, so maybe as it's conveniently still on the board, right, we have some non-effective upper bound for, we know this M of n exists. And so then the second result I want to state is that we have some effective bound, which I guess we don't expect to be sharp, but nonetheless, it's an effective bound. So I have to introduce some notation. So for n at least 1, we let Pn be the largest prime number greater than n plus 1. So then we show that M of n is less than Pn plus 1 times n plus 1. So in particular, M of n is less than 1 plus epsilon n plus 1 squared for n sufficiently large. Okay, so this is some bound. Again, so we don't expect this to be a sharp bound, but it is a bound. And maybe just to give an idea of where this comes from, we use results of Jingsong Xu on P groups acting on rationally connected varieties. And then we use the classification of P pseudo subgroups of the symmetric group. But maybe I'll just note we don't expect this to be sharp. Okay. For some classes of varieties, we do get sharper bounds, which I'll say shortly, but I also want to briefly mention, but not go into much detail, corollary. As a corollary of this, there's some standard local to global argument, is we also get a bound which is roughly n squared for symmetric groups acting on n-dimensional KLT singularities. Okay, and right. But so as I said, yeah. Sorry, thank you so much. Yes, yeah, the smallest prime. Yeah, otherwise this makes no sense. Thank you so much. Yes, yeah, exactly. Okay, great, thank you. Hopefully there are no more typos. Okay. Okay. Right, so this is some bound, which we don't think is sharp, but for some classes of varieties, we're able to get sharp bounds. And so before I write these classes down, I want to give an example. So maybe I'll call this example star. Okay, so I'm just going to write down the notation first. So we let x inside projective space of dimension n plus m. We let this be defined by a bunch of Fermat hypersurfaces. So this is going to be the intersection of degree 1 plus degree 2 plus degree 3 all the way up to degree m. And so then so we're going to take m be the maximal so that x is Fano. So then one can check by computing the Jacobian matrix of this complete intersection that this is smooth. So x is an n-dimensional smooth Fano variety with an Sn plus m plus 1 action. And then one can work out that in this case, n plus m plus 1, the size of the symmetric group, is equal to n plus the ceiling of 1 plus square root of n plus 9 over 2, which we're going to denote sort of suggestively MWCI of n. Okay. Okay, and so as this WCI suggests, the first class of varieties we look at is weighted complete intersections. Okay, so this is theorem 3. So we let x inside projective space, weighted projective space be a quasi-smooth weighted complete intersection. So quasi-smooth just means, so I guess weighted projective space is some quotient of an minus the origin, and so quasi-smooth just means that the pre-image of x before the quotient is smooth. And so if we assume that this weighted complete intersection has a faithful SK action, so then we show that this integer k is less than or equal to MWCI of n, and this bound is sharp. And moreover, we have some description of the maximal examples. So first, if k equals MWCI of n, then x is a finite cover of some variety y inside projective space of MWCI of n minus 1, where y is defined, the ideal of y is defined by symmetric polynomials. And then secondly, if we have a maximal example and the Fano index is maximal, so i.e. where the Fano index means the divisibility of the anti-canonical divisor, then example star is the only example we get. So x is covariantly isomorphic to example star. Okay. All right. So I guess this number of MWCI maybe is a bit mysterious. So maybe let me just first write out a table of some values of this number. So MWCI of n, which is again n plus the ceiling of 1 plus root an plus 9 over 2. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. Okay, so for 1, this is 4, 5, 7, 8, 9, 11, 12, 13, 9, 14, and so on. So I guess one thing you can notice from this list of values is that for n at least 3, this MWCI of n, this is strictly greater than n plus 3. So that's so that is what I alluded to earlier in question 2 prime. And so another thing I want to point out is that for n equals 4, we get 8, which is sort of why we were looking at S8 actions in our result about final fourfolds. Okay, let me not get rid of that. Okay, so let's see, so 20 minutes left. Right, so maybe I'll just very briefly sketch some of the ingredients that go into the proof of theorem 3, because they'll come up, some of these ingredients will come up a little bit in the next result that I want to state, but basically the idea is to use the projective representation theory of the symmetric group and the fact that there are not very many representations. Okay, so the idea of theorem 3. So the first step is, so first we lift automorphisms of X to automorphisms of the ambient weighted projective space. And so then for this weighted projective space, we have this exact sequence from 1 to C star to the automorphisms of some graded ring to the automorphisms of this weighted projective space to 1, where R is some graded ring where the weight of Wi is equal to Ai. And so then this automorphism group, we have some product of GLNs inside this automorphism group of R as the maximal reductive subgroup, where these like LIs, they break up depending on the weights. And basically is what happens is we can get, the idea is that we can get a copy of this SK, or I guess more precisely some short covering of it inside GL, this general linear group, and then we use the projective representation theory of the symmetric group to sort of bound this behavior. And then, right, so where does the final assumption come in? Basically, the final assumption is used in the numerics to say that the codimension is less than dimension. So somehow this becomes useful in the numerics. Right, and so I guess maybe the idea for how we prove for the statement about the maximal examples, basically for the first case, we show that basically this projective space, this is either Pn or P where all the weights except one of them are the same. And then in the second case, we can show that this thing is isomorphic to something in an actual projective space. So this is roughly the idea of here. Okay, so the next result I wanted to state was is for toric varieties, and so the proof uses a lot of similar ideas to the proof of theorem 3. So we let Sk act on an n-dimensional Q factorial toric variety. So then we give some list of the maximal orders of the symmetric group and the optimal examples. So I guess here's n 1, 2, 3, 4, at least 5, 4, 5, 6, 6, and plus 2. So you get P1 cross P1, you get projective space, P4 and P2 cross P2. And in the last case, the optimal example is Pn. So for among simplicial toric varieties, we don't get any better examples than these. And in fact, our examples are sort of, the examples we get are sort of worse in general than what the action you can have on a rational variety. And then I guess, yeah. Not necessarily Fano. Yeah, thanks for the question. Yeah, so this result works for any toric variety. Yeah, because somehow in theorem 3, the Fano assumption is used in the numerics, but in the toric variety case, we can sort of get around this assumption. And then sort of the idea for this is that, so we use results of Cox on the automorphisms of simplicial toric varieties. And basically this breaks into two pieces. Either it acts on the Cox ring, or it acts on the fan. And then in the case of the Cox ring, basically we have some sequence which is sort of similar to the weighted projective space sequence. But the idea is for this case, we can sort of bound these actions using I guess the projective representation theory of symmetric group, or I guess we also need the alternating group. And then in the second case, it turns out we can also bound the actions on the fan using the representation theory of the symmetric group. Yeah, but somehow the final assumption in the WCI case is used in the numerics, but we don't have to deal with these complete intersections in the toric case. So, okay. Right, and so before I had two questions listed on the board. So next I'll move on to question 3. Maybe since I have space here, I won't erase here. So maybe I'll just remind you all. So we saw before we have n+3 acting on this rational n-dimensional Fano in any dimension. And right, so among the toric examples, we don't get any better actions, and we can get larger actions among weighted complete intersections. But somehow, as far as my co-authors and I know, these are the best examples. So I guess question 3 that I'd like to ask is the maximal among weighted complete intersections equal to the maximal among Fanos? So just to so in particular, this is the maximum for fourfolds S8. So this is something we don't know. So Fano. Great. So in the remaining 10 minutes, I'll try to sketch some of the pieces that go into the proof of theorem 1. So the proof of that result uses a lot of very different ingredients than theorems 3 and theorem 4. Okay. Right, so it's the idea of theorem 1. So again, this was the boundedness of SA equivariant final fourfolds. So what we do is we let SA act on X, the Fano variety, and then we let Y be the quotient. And so then we write B for the effective divisor such that when we pull back KY plus BY, we get KX for B an effective divisor. So then this pair Y comma BY, this is a KLT log final pair. And then so how this proof goes is we get several different cases depending on the dimension of the dual complex of this log final pair. So to state this, let me introduce a definition which is due to Joaquin. Okay, so first let me define the co-regularity of a log Calabi-Yau pair. This is trying to be coreg of dimension Y minus dimension of the dual complex minus 1. And so what is this, the dimension, what is this dual complex? Right, so for this, so we take a DLT modification. And so then maybe we get some exceptional divisors. So these are EIs. And so the dual complex of this pair Y comma gamma, this is some CW complex where the vertices correspond to these prime exceptional divisors. And sort of what you glue in a K cell to the CW complex depending on how these exceptional divisors intersect with each other. So in this picture, we have these three vertices corresponding to these three components, and then we have these one cells for the intersection. And so this definition is independent of the choice of the DLT modification. And so for a log final pair, the co-regularity of a log final pair Y comma B is the minimum of the co-regularities of these log Calabi-Yau pairs such that gamma is greater than or equal to B, and Y comma gamma is log Calabi-Yau. Okay. So I can erase this board. And right, so how the proof goes is it breaks up into several cases depending on the co-regularity of this pair. So the first case is the case when the co-regularity of Y BY is equal to 4, i.e. when the dimension of the dual complex is 1. So in this case, this is exceptional. And so then we can use result of Bierkar to show boundedness in this case. Right. And so in the second case, case 2, this is co-regularity of 3. And roughly the idea is we use that S8 doesn't act on a rationally connected threefold, or less than or equal to threefold. Basically to reduce to a case where we know boundedness. Again, using Bierkar's boundedness result. So in these two cases, we show directly that these are bounded. And then in the third case, where the co-regularity is at most 2, this case, we show this doesn't happen, but somehow we need to use a lot of like heavy machinery from topology to show this. So case 3, co-regularity y is at most 2. Okay, so right, so maybe not go into that much detail since I'm almost out of time, but roughly in this case we can use results of Kolar and Xu to get some related variety where we have where the dual complex is a sphere or disk of dimension at most 3, and we can sort of get SA acting on this disk or sphere with this L at most 3. And so then, right, so we can get some sort of action of this, of S8. And so we can upgrade this using results of Pardon on actions on 3 manifolds to get some sort of smooth action of S8. And so then, right, so then we can use a classification, I guess, of symmetric orthogonal actions. To show this doesn't happen. Basically, so I'm sweeping a lot of details under the rug, but the point is that in this case we can force the symmetric group to act on the dual complex in a way such that we get a contradiction if we get some sort of non-trivial action, and then if we right, so if action is non-trivial, and then if it turns out that if we have a trivial action, then we can get an SA action on a lower dimensional rationally connected variety, which by the lower dimensional classification can't happen. So I guess by using a lot of machinery, sort of the upshot is that using a lot of these results in topology, we show this case doesn't happen. But something I wanted to point out, so these results, which I'm not stating very precisely, so these somehow they all use this dimension at most 3, so a lot of these results are not known in higher dimensions. So that's one obstruction to generalizing our boundedness result for to higher dimensions. Okay. Right, so I have 1 minute left, so let me just end by reiterating the questions that I wrote earlier. So I guess maybe it's just to repeat. So question 1 is, are the maximally symmetric Fano varieties of dimension n bounded? Oh, something I should have said earlier is that, right, so that's question 1. I guess we show that this is true if n is at most 4. So something else I should have mentioned earlier is that it sort of matters that we're using this very non-abelian symmetric group. For example, if you replace Sn by some abelian group, this is no longer, this boundedness result is no longer true. And then I guess question 2 is, are the maximally symmetric n-dimensional and at least 3 Fanos irrational? So this is yes for n equals 3 by Boville. And so even in our 2 examples for dimension 4, we don't know the rationality of these varieties. Right. So furthermore, maybe a question to double prime is, in any dimension n, do there exist irrational maximally symmetric Fanos? This is also something we don't know. And sort of the reason, a reason for this is that it seems that the numerics for smoothness are quite complicated. So one thing you could try to do is, so it's a fact due to the result of Zhuang that if you take a index 1 smooth complete intersection of large enough dimension, that will be rationally rigid, so it will be irrational. But one issue is if you try to modify example star to get something of index 1, in general, you no longer get something smooth if you don't just take the first m degree equation. So smoothness is some sort of issue for question 2 double prime. And then finally, to repeat, question 3 is mn equal to mwci of n. So this is something we don't know, but as far as we know, there aren't any better examples than the weighted complete intersections. Yeah, so if anybody has any ideas about any of these questions, I think Joaquin and I would be super interested to talk. So thanks a lot for your attention. That's everything I wanted to say.